recalling this. And Unit 2 is going to start with compounds. So we have compounds down here. Come on. It's mad. Gosh, are you serious? All right. Okay. Goodness gracious. So we said that a compound can be broken down into its elements using some sort of, I'll put CHM165. What's that stand for? Chemical reaction. Very good. We can take a compound, break it down into, like water, we can break down to hydrogen, oxygen via some chemical reaction. We can take the elements and build them up by some sort of chemical reaction into a compound. Okay, so compounds, like the slide says, and this is kind of a review slide, you need to have 2 or more elements that have chemical bonds between them. So I tried again this afternoon to try to get this video to play, and it did not play. So, sorry. So this is kind of a review slide again. These, you recognize the elements, okay? And so these are examples of compounds. So we use chemical formulas to represent or to say what the repeating unit is within a compound. Let's pick on ammonium sulfide. So are we good with this? Oh, I better put the lid on that. That's not going to work. How many hydrogens are in a repeating unit of ammonium sulfide?
8.
There are 8. And why is there 8? Yeah, exactly. The fact that we have NH4 ammonium in parentheses and a 2 outside means that we have 2 NH4 units. So thus we have 8 hydrogen atoms. Very good. And I think I mentioned this before, that compounds, actually there's 2 types of compounds. There are ionic, or I think I'll start with molecular compounds. And I think somebody said, is that the same thing as covalent? And that is. Molecular or covalent compounds. I can't spell covalent, something like that. And then we have ionic compounds. And we'll be talking more about these in this unit. And I know it's kind of small, but I usually actually start kind of a tabulation of comparing and contrasting those 2 types of compounds. I just think it's kind of helpful. First off, we have something to add. Molecular compounds, and I think I talked about this before, we call that repeating unit a molecule. And if you want to make sure you know you're really cool, if you have an ionic compound and if you've isolated one repeating unit, that's a formula unit. Put another way, the word molecule is overused. Okay. So examples of molecular compounds, we have methane, ammonia, and water. So I think I mentioned this before. I kind of think of molecular compounds, molecules of molecular compounds, is basically they're their own little entity. You can take, you can isolate them and you know which atoms belong with which entity. Okay. Acetic acid has 2 carbons, 4 hydrogens, and 2 oxygens. We can kind of show it has a little bit of structure. Okay, here is acetic acid. So acetic acid, along with methane and ammonia and water. Acetic acid is also an example of a compound that is a molecular compound. And these don't play either. I will go ahead and kind of animate this one for you. Okay, this little one. So the opposite of molecular compounds are ionic compounds. I have a slide, and I'm going to go ahead and add it up here right now. You know you have a formula of a compound that's an ionic compound if you find a metal in it. Okay? So I'm going to say metal, contains metal. How do we look at a periodic table and know where the metals are? very good. They're last of the step. Yep, metals, okay. So you guys would tell me that table salt is sodium chloride, Na1Cl1. So sodium chloride, sodium is a metal. So that must be an ionic compound, and it is. So, like I said, to kind of animate this, and we'll be talking more about this later, but just kind of an introduction. Here we have a metal. So what's chlorine? And don't be shy about finding chlorine on the periodic table. What is chlorine, metal or non-metal?
Non-metal.
It is a non-metal.
Yeah.
Find it on the periodic table. It's on the right of the JAG. Yep. So metals tend to give up electrons. So I'll show a little electron being transferred there. And nonmetals tend to take in electrons, like chlorine is taking in an electron. And then we talked about when a neutral atom loses an electron, it becomes charged. Does it become positively charged or negatively charged if it loses it? Positively charged. Very good. Exactly. And there is a bit about quantity, like how many electrons do the metals or electrons do they want to lose? We'll be talking more about that. But sodium wants to lose one electron. Chlorine brings in one electron, okay, and it becomes negatively charged. Starts with the letter A. What do we call a negatively charged?
Anion.
Ion. An anion. Very good. Anion. Yep. So ion is generic. Anion is negatively charged. What do we call positively charged ion? Cation. Very good. But anyway, and I'll go ahead and add this, for ionic compounds, they must contain at least one, what we call ionic chemical bond. So under here, I'm going to write contains metal, and I'm just going to say has ionic chemical bond. So as I've drawn that cation, sodium cation, and that chlorine or chloride anion, I'm going to go ahead and do a little, what color do I want? I'll go with blue. Dot, 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 dot. That is my ionic bond. Okay. So that would have been my little animation. So an electron is transferred from the metal to the nonmetal. In doing so, now the metal's positively charged, the nonmetal's negatively charged, and they have a dot, 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 dot electro attraction towards each other. Okay, so again, if you have the formula for something, you're like, yeah, is that ionic or is it molecular or covalent? Well, if it has a metal, ionic. And that will do it for most, probably 98% of the time. So one of the things about ionic compounds is they form crystal and lattice structures. I'm running out of room here. So I'll put crystal and lattice structures. Crystalline lattice structures. So remember how I said that the molecular compounds, the molecules, you could put your hand around it. Like if you have a water molecule, you know where the one oxygen and the two hydrogens are. If you have methane, you know where the carbon and the four hydrogens are. It's like you can sink your teeth into it. If you look at this right here, this crystal lattice structure, you're like, oh, I know it alternates cation, anion, cation, anion. But like for every one anion, for instance, in this case, we have 6 cations that it's connected to. So you're like, so we call a isolated repeating unit of an ionic compound, we call it a formula unit. What's the abbreviation for formula unit? It is FU. It really is. Just makes me giggle. So yeah, sodium, or I'll go ahead and up here, I'm running out of room, but for ionic compound, I'll go ahead and put example, NaCl, look for the metal. Molecular compounds, I'll put example, H2O. All right. So, I've already written this on here. In general, metals bonded with nonmetals. So metals bonded with nonmetals, sodium bonded with chlorine, make ionic compounds. If you have all nonmetals, and if you're like me, that makes me pause, because periodic table, which you got more of, metals or nonmetals? We have a lot more metals. But our molecular compounds are basically your nonmetals that are bonding together.
What about the metalloids?
Metalloids, I think I'd probably go with which side of the jag they're on. That's a good question. But in theory, they could go either way. What I thought you were going to ask, and this is another question, do you remember where I put hydrogen? Actually, my black and white periodic tables have hydrogen two places. They have them in the upper right-hand corner and the upper left-hand corner. Hydrogen's there twice. So hydrogen, for all intensive purposes, is a nonmetal. So here, under molecular compounds, I'm going to say H equals nonmetal. And that will usually get you down the road. Okay. There won't be a homework that's due on Friday, but on Friday, after we go over your test kind of quickly, Friday we'll pick up lecture and there will be a couple assignments due. People usually do pretty good with this. The molecular weight, the weight of a molecule, okay? Basically, all you got to do is you'll have a periodic table. I will have you not have to calculate molecular weights without a periodic table. So remember, periodic table for each element gives you an average atomic weight. So the weight of the whole molecule then is you just add them up. Okay. So what are the units of average atomic weight? The weight of an atom. AMUs, perfect, yes. We use AMUs. So we also use AMUs for molecular weight. It's not too bad. Well, the only difference between molecular weight and formula weight, what's the difference? I'll give you this hint up here. What's the difference between molecular weight and formula weight? Exactly. A formula weight means that you're dealing with a compound that's an ionic compound, but you calculate it the same way. Exactly the same way. Molecular weight, formula weight. I'll put molecules. I'll put MW for molecular weight. I'll put FW for formula weight. All right. So let's work a problem. We could deal with hydrazine, N2H4. I think that's, yeah. That's a nitrogen with a double bond to another nitrogen, and then we have the 4 hydrogens sticking out of the nitrogen. We're supposed to knock out how much does a molecule weigh, what's its molecular weight. So this is one where you just go to the periodic table. I take 2 times the decimal number for nitrogen, which is 14.01. Units would be AMUs, so 2 times 14.01 AMUs, because it's N2, and then it's H4. So I take 4 times 1.008 to represent the mass that's brought by the 4 hydrogens. Okay. Now, these 2 and the 4 are exact. Of course, there is uncertainty in the average atomic weight. And I'm going to tell you that usually if you have something that's 9 or lighter, then I'm going to want you to go with 3 decimals, okay? So hydrogen falls under that category, so we have 3 decimals. Anything that's heavier than 9, go with just probably 2 decimals. So basically, this kind of becomes like an addition problem, where we're taking 14.01 twice, plus 1.008 4 times, and we round according to decimals, which is 2. That's it. Any questions about that one? Okay, so that was that was a molecular weight. Let's go with the formula weight. We just need to go out and find an ionic compound. So what is the metal in calcium nitrate?
Calcium.
Calcium, very good. Calcium's definitely 2A. Okay. What's another name for 2A elements?
Alkaline earth metal.
They are alkaline earth metals. Very good. Okay, so we'll have a periodic table. How many oxygens do we have here?
6.
Very good. 6 oxygens. You got it. So we'll go to the periodic table. Take 1 times 40.08. That represents the calcium. Plus 2 times 14.01 AMUs. That represents the nitrogen. Plus 6 times 16.001 AMUs. That represents the oxygen. Round according to 2 decimals, because it's kind of like one big hairy addition problem. And we got a formula weight of this ionic compound is 164.10 AMUs. And remember, I already told you that if you just put U there, that's cool, because that's the new way of doing it. The new in the last 10 years, right? So U or AMUs, that's great. See, we could do these all day. Okay, so if you're okay with molecular weight and formula weight, well, we tackled something in Unit 1 called molar mass, and it's another one of those things. What does it mean? Well, it means the mass of 1 mole. And so what you guys have been doing for your homework, quite well by the way, is coming up with the molar mass for the elements. And it's the decimal number, it's the average atomic weight, but it's grams per 1 mole for that element. Okay? So, molar mass for the compounds are going to be similar. The molar mass for atoms is numerically the same thing as the average atomic weight, except then it's grams per mole. Molar mass for molecular compounds is the molecular weight, bless you, but instead of units of AMUs, it's grams per mole. Molar mass for ionic compounds is that formula weight, but instead of AMUs, so it's numerically equivalent, but instead of AMUs, it's grams per mole for that compound. Very good. You don't seem like you need convincing. So these problems that we're going to do are very similar to the moles to grams or grams to moles problem you guys did for the elements, except now it's for compounds. So we're going to do a couple of not conversion problems. Now, this almost seems silly to me. So we're going to knock out the molar mass for these 2 compounds. Remember I said that look for the metal, and that'll get you down the road maybe 95, 98% of the way. If you find a metal, it's an ionic compound. Okay. Now I'm here to tell you that ammonium chloride is an ionic compound. And if you look at it, you're like Mrs. Snipes. Let me find a periodic table, let me find nitrogen. And I would find nitrogen as clearly a nonmetal. Hydrogen, I told you, nonmetal. Okay, and then that just leaves chlorine. Chlorine, definitely on that side of the jag. It's also a nonmetal. These are all nonmetals. Okay, the reason it's an ionic compound, and some of you are already very familiar with this, is it actually has a polyatomic ion. This is ammonium. Okay, it's a polyatomic ion. So, and we'll be talking more about this. All that means is we have that ammonium ion, we have this chloride, negatively charged anion, and then we have the dot, 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 dot. That is an ionic bond. And I said, or what I meant to say is if you have any ionic chemical bonds in your compound, then you have an ionic compound. It's like contaminated. So bottom line, it's an ionic compound. But ethane, it's a molecular compound. All right, but that wasn't the point. The point here is to come up with the molar masses. What are the molar masses of these things? So I'm going to show you, don't write this down if you don't want to. The next slide's a lot better, okay? The word explicit means to add detail, in this case detail that I wouldn't usually add. So for the methane, C2H6, we need to account for the carbon. So I have 2 moles of carbon atoms in 1 mole of C2H6. For carbon, it weighs 12.01 grams for every 1 mole of carbon. And then I can write something for the hydrogen term. The formula says that I've got 2 carbons and 6 hydrogens. So I have 6 moles of hydrogen atoms for every 1 mole of the compound, C2H6. From the periodic table, we know that for hydrogen, we have 1.008 grams of hydrogen for every 1 mole of hydrogen. So factor label-wise, all I've done here, and kind of breaking out this way, is my moles of carbon cancel. Okay, I'm left with grams of carbon per 1 mole of methane or ethane, and here moles of hydrogen cancel. I'm left with grams of hydrogen per 1 mole of compound. So bottom line is when we add those 2 masses, we get the total mass per mole of compound. So again, the 2 and the 6 are exact. They bring no uncertainty. So basically, we're kind of aligning with the decimal and rounding according to fewest decimals, which is 2. So 30.07 is the number we get. Units would be grams of C2H6 per mole of the compound.
So this is the exact same as figuring out the AMUs, right?
Exactly.
So it's the exact same.
It's exact same thing as coming up with the molecular weight, but now it's
way
grams
easier
per
to
mole
write
instead of
down
AMUs. Right. So that's explicitly written, exactly. And let me tell you, when I do this calculation, this is what I do. And kind of exactly along the lines of what you were saying, Mike. I'm a stickler, and I think a chemistry teacher should be, I think all physical science teachers should be, for showing all your work. So you're going to have to show me how you came up with the molar mass for that compound. And like Mike said, you're just going to take 2 times the decimal number of carbon plus 6 times the decimal number for hydrogen. That's it. Okay, and that's exactly what I'm showing up here. 2 times 12.01 plus 6 times 1.00, sorry, plus 6 times 1.008. Yeah. And then I slap on, this is one of those where I just slap on grams per mole, molar mass. Okay, if I were coming up with a molecular weight, it would be the same number, but it would be AMUs, right? Yeah, okay.
One question on this slide before, when you have like a gram over the mole C2H6, can you put that C2H6 after that, can't you? So
Yes.
it's like grams per mole of the whole thing, right? I was just making sure.
Yeah, yeah. Are you saying, like do 30.07 grams per mole of C2?
I guess what I was thinking of was like, I do like you did, except where the mole was, I'd stop at the word mole, go over the next space and put CH next
Yeah.
to it.
Yeah, that would be
better?
fine. Yeah, that's
Okay.
fine. Yeah, so you're just identifying the compound in the end there. Yep.
Changing the formula there accidentally.
Yeah. So you would say grams per mole of C2H6, right? Yeah. Yep, that's fine. You got it. Okay. Let's see what else we got. Ionic compound. Okay, so molar mass of the ionic compound, it's going to look very similar to the formula weight of ammonium chloride. And I'm going to do the non-explicit one. How's that? Okay. So I need to account for my nitrogen. So 1 times 14.01. I need to account for my chlorine. Wait. Is that right? No, hydrogens. NH4Cl. So I have 4 hydrogens, 4 times 1.008 and then I need to account for my chlorine. There's only one, and the decimal number for chlorine is 35.45. This is one of those, like I said, and you need to show this. I know a lot of times students are like, oh, I can just plug in my calculator and then just use it, but you have to show this calculation. Actually, it can save your butt, because if you put your, if you just do a number wrong, you can show me that this is your molar mass, and it might be wrong, but then I can see how you use it. And so for this sort of problem, we're rounding according to decimals, basically, because it's one big old addition problem. And so for adding, then we need to round according to decimals. So we have 2 decimals in the first term, 3 in the second, and 2 in the third. Okay, so we round according to 2 decimals. Any questions? Ammonium chloride, the molar mass is 53.49 grams per 1 mole. Cool. And this is kind of what I've been saying. The kind of the rule of thumb, the 3 decimals if it's light, the 2 decimals if it's heavier than 9. And the tipping point, as it turns out, is about atomic number 4 and 5. Okay, so that's between beryllium and boron. Okay. So for hydrogen, helium, lithium, beryllium, we go 3 decimals. And for boron or heavier, we go 2 decimals. All right. Well, let's go ahead and do a problem with compounds, mass to moles and moles to mass conversion. So if you guys have this one, this is just a review slide. I don't think you do. This should be kind of hot in your memory. What's today, Wednesday? I'm thinking this was Friday. So for the compounds, we get their molar mass by their average atomic weight. So we picked on calcium in class, and we said the decimal number for calcium is 40.08. And we said that means for calcium, there's 40.08 grams per mole, molar mass. So let's take it up a notch, and let's go to compounds now. Not just elements, but compounds. And we've been talking about how do you get the molar mass of a compound. So we're going to pick on chloroform, which we got non-metal in carbon, non-metal in hydrogen, non-metal in chlorine. So that would be a molecular compound. So how many moles? The stuff in brackets won't necessarily be there, so it will just simply read how many moles is 1.28 grams of chloroform. So you're going to have to show me knocking out the molar mass. And do it the abbreviated way. I think I would. So we take 1 times the decimal number for carbon, which is 12.01, plus 1 times the decimal number for hydrogen, 1.008, plus 3 times the decimal number for chlorine. That's kind of getting a heavy little sucker. 35.45. Rounded to 2 decimals. We got a molar mass to use in this problem of 119.37 grams per mole. Sometimes students say, well, Mrs. Snipes, do I really need those 1, like the 1 for carbon and the 1 for hydrogen? I think it's a good habit, because then you're like, you know how many there are, and it just kind of makes sense. So what's our first term going to be?
1.28.
Very good, 1.28 grams over 1. And then, how can we use the molar mass to make grams cancel and be left with units of moles?
1 mole over 119.37 grams.
Yep, everybody buy that? 1 mole over 119.37 grams. That's that physical property. That's the molar mass of chloroform right here. So grams cancel, we have units of moles, which is perfect. So how many sig figs we need to round to?
3.
3. Yep. Sure. Very good. Did you get this? 0.0107. Units, of course, would be moles. Sometimes students would say, well, Mrs. Snipes, shouldn't you say moles of CHCl3? And yeah, that would be good, but I don't have to because I'm only dealing with one compound. When we do other calculations, we'll actually have at least a couple compounds in play. If there's one compound, we don't have to. Any questions? So that's just kind of like a review for the problems that you're doing with elements. So let's do one more problem, and this would be, that was a mass to moles, this is a moles to mass problem. So we're dealing with methane again. So we need to knock out in the margins what the molar mass of methane is. So 1 times 12.01 for carbon, representing the carbon, plus 4 times 1.008 to represent the hydrogen. And then round to 2 decimals, that gives you a molar mass for the compound is 16.04 grams per mole. Physical property, molar mass of methane. So what's our first term going to be? 0.444 moles over 1. Sometimes these problems are so fun coming up with just the bogus numbers to start out with. The next number is not bogus though. So how do we let moles cancel? We left with units of grams.
16.04 grams over 1 mole.
Do a mole in the bottom. Yep, 16.04 grams over 1 mole. You're both right. Cool. So moles cancel. And then we need to round it according to how many sig figs?
3.
4. Yep. I'm liking 4. Voila. 7.129 grams. Or 7.129 grams of CH4. What do you think? See, I didn't think it hurt your brain too much. Well, that's where I wanted to get to. So that's it for today, and we'll pick up there and knock out this part. Maybe go to part 2 even on Friday. So we'll see. Okay? Yay.